Hello there, and welcome to Smart Student TV, the only channel where academic and professional prowess is nurtured right from the comfort of your living room. Whether you are a student striving for excellence, a professional looking to sharpen your skills, or simply a lifelong learner, you are in the right place. In today's tutorial, we dive into a fascinating and indispensable world of cryogens and cryogenic technology. This is not just another scientific concept. It is the gateway to unlocking some of humanity's most remarkable achievements. Imagine materials so cold that they defy the usual laws of physics, gases turned into liquids that can power rockets, or temperatures so low that they allow scientists to glimpse the building blocks of matter. From the preservation of vital biological samples in hospitals to fueling spacecraft that explore the farthest reaches of our universe, cryogens silently but powerfully shape our world. So, fasten your seatbelts as we embark on an exciting journey into this frozen frontier. Introduction to cryogens and cryogenic technology. Cryogens are substances that exist as liquids at extremely low temperatures. The most common cryogens include liquid nitrogen, widely used in food preservation and medical freezing; liquid helium, crucial for cooling superconducting magnets in MRI machines; liquid oxygen, a key component in rocket fuel; and liquid hydrogen, another critical rocket propellant and a source of clean energy. These substances share unique properties such as extremely low boiling points, high expansion ratios upon vaporization, and either non-flammable or highly reactive characteristics, depending on the specific cryogen. Their ability to absorb significant amounts of heat makes them ideal for cooling applications. Beyond these properties, cryogens serve essential purposes in fields such as medicine, e.g., cryosurgery and tissue preservation, space exploration as rocket propellants, and the food industry for rapid freezing and preservation of perishables. Each of these uses leverages the exceptional thermal and chemical properties of cryogens to achieve outcomes otherwise impossible under normal temperature conditions. Objectives of this tutorial. By the end of this tutorial, you should be able to 1. Define cryogens and cryogenic technology. 2. Identify examples of commonly used cryogens. 3. Understand the general importance of cryogenic technology. 4. Describe its importance in laboratory applications. 5. Explore the various applications of cryogenic technology. 6. Discuss the types, production, handling, and storage of cryogens. 7. Understand the safety measures and disposal methods for cryogens. General importance of cryogenic technology. Cryogenic technology plays a vital role in various fields, including 1. Preservation of biological samples, such as blood, tissues, and reproductive cells. 2. Cooling superconducting magnets used in MRI machines and particle accelerators. 3. Enabling space exploration through rocket propellants. 4. Enhancing industrial processes such as gas separation and liquefaction. Importance in the laboratory. In laboratory settings, cryogens are essential for 1. Storing biological and chemical samples at ultra-low temperatures. 2. Supporting experiments requiring extremely low thermal energy. 3. Facilitating advanced research in physics, chemistry, and biology. 4. Calibrating temperature-sensitive instruments. Applications of cryogenic technology. Cryogens aren't limited to laboratories or space shuttles. They have applications in everyday fields too. 1. Medical field. Cryosurgery, where extremely cold temperatures are used to destroy abnormal tissues, and MRI machines, which rely on liquid helium to function. 2. Food industry. Ever noticed how frozen foods retain their freshness and texture? That's often thanks to cryogenic freezing. 3. Space exploration. Rockets wouldn't fly without liquid hydrogen and liquid oxygen as fuel. 4. Electronics. Superconductors, used in advanced computers and scientific equipment, are cooled using cryogens. 5. Energy sector. Liquefied natural gas, LNG, is transported and stored at cryogenic temperatures. Types of cryogens and their properties. Introduction to cryogens. Cryogens are super-cold liquids used to achieve extremely low temperatures, usually below -150 degrees Celsius. They are incredibly important in industries like healthcare, space exploration, food preservation, and scientific research. In this tutorial, we are going to talk about 4 common cryogens: liquid nitrogen, liquid helium, liquid oxygen, and solid carbon dioxide. We'll keep it simple, explain everything clearly, and use examples to make it easy to understand. 1. Liquid nitrogen. Liquid nitrogen is one of the most commonly used cryogens. It boils at -196 degrees Celsius, which is unimaginably cold. It's a colorless and odorless liquid that doesn't catch fire and doesn't react with most materials. People use liquid nitrogen in so many ways. For example, in the food industry, it's used to quickly freeze fruits, vegetables, and even meats so they stay fresh for a long time. In medicine, it helps preserve biological samples like blood, tissues, and even vaccines. You might have also heard about cryotherapy, where liquid nitrogen is used to treat skin conditions like warts. It's also used in industries for tasks like shrink-fitting metal parts or cooling superconducting systems. Imagine this. A scientist in a lab needs to store important samples for years. They pour liquid nitrogen into special storage containers called dewars, and the samples stay frozen and perfectly preserved. 2. Liquid helium. Liquid helium is even colder than liquid nitrogen. In fact, it has the lowest boiling point of any element at -269 degrees Celsius. It's a very light and non-flammable liquid. One of the biggest uses of liquid helium is in MRI machines. These machines use powerful magnets that need to stay super cold to work properly, and liquid helium does the job perfectly. Scientists also love liquid helium because it helps them study how materials behave at extremely low temperatures. In space technology, it cools down sensitive instruments like infrared detectors. Think about an MRI machine in a hospital. Inside, there's liquid helium keeping the magnets so cold that they can create clear and accurate images of a patient's body. 3. Liquid oxygen. Liquid oxygen, or LOX, is another important cryogen. It has a boiling point of -183 degrees Celsius and has a pale blue color. Unlike nitrogen and helium, liquid oxygen is a strong oxidizer, which means it can make other materials burn more intensely. Because of this, it's widely used in rocket engines as an oxidizer to help fuel burn efficiently. It's also used in hospitals and emergency services to provide oxygen to patients who have difficulty breathing. In addition, industries use liquid oxygen for cutting and welding metals. Imagine a space rocket ready for launch. Inside its fuel tanks, there's liquid oxygen and liquid hydrogen. When the rocket engines ignite, the two combine to create an explosive reaction that sends the rocket soaring into space. 4. Solid carbon dioxide, dry ice. While not strictly a cryogen in its liquid form, solid carbon dioxide, commonly known as dry ice, is another important substance used for cooling. Dry ice is the solid form of carbon dioxide, and it is extremely cold with a temperature of -78.5 degrees Celsius. It sublimates directly from a solid to a gas, bypassing the liquid state entirely. Production of cryogens. When it comes to making cryogens, there are 2 main approaches: small-scale production in laboratories and large-scale industrial production. In a laboratory, scientists use small liquefaction systems. These systems work by compressing gases and then rapidly expanding them, which causes them to cool down and turn into liquids. For example, nitrogen gas can be turned into liquid nitrogen using this method. On an industrial scale, things get much bigger and more complex. Air separation plants are used to produce cryogens like nitrogen and oxygen. The air is first cooled down to extremely low temperatures, and then the gases are separated based on their boiling points. This process is called cryogenic distillation. Cooling cycles, such as the Joule-Thomson effect, are also used to achieve these ultra-low temperatures. Imagine a massive factory with tall towers and pipes everywhere. Inside these towers, the air is being cooled, separated, and turned into liquid nitrogen, liquid oxygen, and even argon. Handling, storage, and transportation of cryogens. Cryogens, or cryogenic liquids, are substances that exist at extremely low temperatures. These include liquefied gases such as oxygen, nitrogen, argon, and carbon dioxide. While cryogens have essential uses across various industries like medical, industrial, and research applications, they also present unique hazards. Understanding how to handle, store, transport, and dispose of cryogens safely is crucial in preventing accidents and ensuring the safety of both people and the environment. Cryogenic containers. The basics. Cryogenic containers are typically vacuum-insulated flasks, called Dewar flasks, designed to hold liquefied gases at extremely low temperatures. These containers are built to keep the cryogenic substance insulated from the external environment, preventing heat from entering the container, which would cause the liquid to evaporate and expand rapidly. Imagine a thermos bottle but designed to hold gases like liquid nitrogen at temperatures that are far colder than anything found in your freezer. These containers are constructed using materials that can withstand intense cold, and they usually have multiple layers of insulation to maintain the low temperature of the cryogen. There are various types of cryogenic containers, ranging from small, portable flasks used for medical applications like cryopreservation, to large tanks that are used to store and transport liquefied gases in industrial settings. Some of the more common cryogenic containers are Dewar flasks, which are commonly used in laboratories and hospitals, and large cryogenic tanks used in industries such as welding, steel manufacturing, and aerospace. Proper labeling and monitoring. Labeling and monitoring are two crucial aspects of safely handling cryogens. Cryogenic containers must be clearly labeled with the contents and the temperature of the cryogenic substance inside. Labels should also include hazard warnings, such as the potential for asphyxiation, fire hazards, or the risk of explosion. This helps anyone who comes into contact with the container understand what they are dealing with and take appropriate precautions. Moreover, monitoring is critical when dealing with cryogens. Regular checks should be made to monitor the temperature, pressure, and integrity of the container. Specialized monitoring devices that track these factors should be in place to ensure that the cryogen remains within its required parameters. For example, a liquid oxygen tank might have a pressure relief valve that automatically releases gas if the pressure becomes too high. Monitoring this pressure regularly ensures that such devices function as intended. Transporting cryogens. Transporting cryogenic substances involves unique challenges because of their extremely low temperatures. Cryogenic liquids require specialized vehicles designed to maintain these low temperatures during transport. These vehicles are typically insulated and equipped with refrigeration systems to keep the contents cold. For example, cryogenic tankers used in the transportation of liquid nitrogen or oxygen are often fitted with insulated tanks and mechanisms that control the rate of heat exchange to prevent the liquid from evaporating. In addition to specialized vehicles, transporting cryogens also involves strict protocols to ensure that they are handled safely. The containers need to be securely fastened and positioned to prevent accidents. Cryogens should not be exposed to heat or open flames, as they can rapidly evaporate and increase in pressure, leading to dangerous situations. It is also essential to have a trained professional oversee the process. These professionals must be knowledgeable about the properties of the cryogen being transported and the best safety practices for dealing with any emergencies that may arise. Hazards associated with cryogens. Working with cryogens presents several hazards that need to be understood and mitigated. These hazards include frostbite, asphyxiation, and even explosions. 1. Frostbite and cold burns. Cryogens are stored at temperatures far colder than what the human body is accustomed to. If a cryogenic substance comes into contact with the skin, it can cause severe frostbite or cold burns. Frostbite occurs when the skin and underlying tissues freeze, leading to tissue damage. For example, liquid nitrogen, which boils at a temperature of -196 degrees Celsius, can cause instant frostbite if spilled on the skin. Cryogenic burns may seem like a common misconception since we usually think of burns as caused by heat. However, cold burns are just as dangerous, and the damage can be as severe as burns from hot objects or liquids. 2. Asphyxiation due to oxygen displacement. Another serious hazard associated with cryogens is the risk of asphyxiation. Cryogenic gases like nitrogen and carbon dioxide are odorless and colorless. When these gases evaporate, they displace oxygen in the air, which can lead to a dangerous environment where there is not enough oxygen to breathe. This is especially true in enclosed spaces like storage rooms or transport vehicles. For example, in a confined space, If liquid nitrogen evaporates and fills the room, it can quickly reduce the amount of breathable oxygen in the air. People in that space could lose consciousness or, in extreme cases, suffocate. To avoid asphyxiation, cryogenic storage areas should always have proper ventilation, and workers should wear oxygen monitors to detect any drops in oxygen levels. 3. Explosion risks. One of the most critical risks when dealing with cryogens is the potential for explosions. Cryogenic gases are in liquid form at extremely low temperatures but rapidly expand as they warm up. For example, liquid nitrogen expands when it turns into a gas. If this gas is not allowed to escape, pressure can build up inside the container, leading to an explosion. This risk is especially relevant in poorly maintained or improperly sealed cryogenic containers. If the safety valves or pressure relief mechanisms fail, the pressure inside the container can rise dangerously high, resulting in an explosion. Therefore, it's essential to regularly inspect and maintain cryogenic containers to ensure they are in good condition. Safety precautions. To minimize the risks associated with handling cryogens, it is important to implement several safety precautions. These precautions are designed to protect both the workers handling the cryogens and the people around them. One of the most important safety measures is the use of personal protective equipment, PPE. PPE for handling cryogens includes insulated gloves, face shields, and protective clothing. These items are designed to prevent direct contact with the cryogen and provide a barrier to protect the skin from frostbite or burns. For example, when handling liquid nitrogen, workers should wear thick gloves made of materials designed to withstand extreme cold. Face shields and safety goggles can protect the eyes from splashes, which could cause severe injuries. Adequate ventilation in cryogenic storage areas. Cryogenic gases should always be stored in well-ventilated areas to prevent the risk of asphyxiation. Adequate ventilation helps ensure that any gas released from the cryogen can safely disperse into the atmosphere without reducing the oxygen levels in the room. Cryogenic storage areas should be equipped with ventilation systems that can circulate air and remove any excess gas. For instance, a storage room for liquid nitrogen should have high-capacity fans to maintain airflow and prevent oxygen displacement. Regular equipment maintenance and inspections. To ensure the safe operation of cryogenic containers, regular maintenance and inspections are essential. Equipment such as pressure relief valves, monitoring systems, and insulation should be inspected for signs of wear and tear. Regular maintenance checks help identify and fix problems before they become serious hazards. For example, a cryogenic storage tank used in an industrial facility should undergo routine inspections to check for leaks or cracks. The integrity of the insulation must also be checked to ensure it is still effective in keeping the temperature low. Disposal of cryogens. Responsible handling. The disposal of cryogens must be handled carefully to prevent accidents and environmental harm. Cryogenic gases should never be released into the atmosphere without considering the safety implications. Improper disposal can lead to the rapid expansion of gases, creating dangerous pressure situations or contributing to environmental pollution. Controlled venting in well-ventilated areas. Controlled venting is one method used to safely dispose of cryogenic gases. In this process, the cryogenic liquid is allowed to evaporate and vent in a controlled manner into a well-ventilated area. This ensures that the gas disperses into the atmosphere safely without displacing oxygen or creating explosive conditions. For example, liquid nitrogen can be vented into the open air, where it will quickly evaporate and disperse without posing a hazard to the environment. This should only be done in open spaces with proper ventilation to avoid any risk to people. Following environmental and safety regulations. It is essential to follow environmental and safety regulations when disposing of cryogens. Various regulatory bodies, such as OSHA, Occupational Safety and Health Administration, and local environmental agencies, have guidelines for the proper disposal of cryogenic substances. Compliance with these regulations helps protect both workers and the environment. In conclusion, cryogens are incredibly useful but also come with significant risks. To safely handle, store, transport, and dispose of these substances, it is essential to follow strict safety guidelines and take the necessary precautions. This includes proper labeling and monitoring, using specialized vehicles for transportation, wearing personal protective equipment, ensuring adequate ventilation, and conducting regular inspections of cryogenic containers. By understanding the hazards associated with cryogens and taking proactive measures to mitigate these risks, we can safely manage cryogens and protect both people and the environment.